Good morning or good afternoon, depending on where you are at. My name is Atar Azizi Namini. I'm director of the ABC UTC at Florida International University. I also wanted to just to mention that 12 years ago, March 2011, we started broadcasting our first monthly webinar. So 12 years from 2011, we are happy that we are continuing these monthly webinars without any interruption. So I thought to mention that up front, it's really something to celebrate. We also like to share with you a very good news. Late in the February of this year, 2023, in an extremely competitive process, the USDOT selected the several UTCs. In Tier 1, they selected 20 Tier 1. We are delighted to tell you that the proposal that we submitted to continue our work, but with a different focus, was selected. So it's an honor to continue serving the bridge industry, but also ourselves at FIU and also our partner university understand fully that this comes with a big responsibility with the bridge industry in the US. So we are delighted to be selected to continue our operations until 2029. But with that, we fully understand that we have a big responsibility, big shoes to fill, and we promise that we are going to do our best. Our partner universities are Florida A&M University, Texas A&M University, University of Georgia, University of Nevada, Reno, University of Oklahoma, and University of Washington. This time, our activities really is going to be focusing to bring all the latest technology, the innovations into the bridge engineering and make sure that the bridge industry in the US is absolutely #1 in the world. That's going to be our focus. It's going to be beyond the ABC. It will include the ABC, but the next generation of the ABC, but bringing all the innovations and all the innovative concepts with bridge engineering. So we are very delighted to be able to serve the bridge community for another several years.
Our presentation today features incremental launching of bridges. We'd like to thank Mike Como, Chief Bridge Engineer with CHA Consulting, Inc., and member of the ABC UTC Advisory Committee for coordinating this presentation. We're pleased to welcome our presenter, Chiara Rosignoli, Senior Structural Engineer with H&H. Also, would like to introduce our Q&A session moderators, Paul Lyles, formerly Georgia State Bridge Engineer, and Jugesh Kapoor with WSP USA and formerly State Bridge Engineer at WashDOT. We'll now begin the featured presentation. Chiara?
Thank you, Marilu, and thank you everyone for attending this webinar. So today we will talk about incremental launching of bridges. We will discuss what is this construction technique. We will focus on incremental launching of cast-in-place concrete bridges. We will then compare this construction technique with other construction techniques that are suitable for similar span lengths. We will take a look at some limitations of the applications of incremental launching and then some example of application, including some very unique bridges. So incremental launching was born in Europe in the 60s, but it became way more popular with the advancement in the knowledge of material. Especially the introduction of Teflon was a game changer for this construction technique because it ended up replacing elements that were greased with motor oil. So it made sliding bridges way easier. This construction technique is now widely used all over the world, and it is also used in the US. If we want to mention two memorable bridges, for steel bridges, we can see the approach span of the new New York Bridge. There are actually some very interesting videos online of this launch. And for post-tension concrete bridges, the Bel Air Causeway. That was built in Florida. So this picture shows you most of the key elements of incremental launching. The bridge is built behind the abutment and then is progressively launched into position. The construction itself, it is simple and it is repetitive, and the equipment that is needed, you can take a peek here, is fairly inexpensive compared to other construction techniques, but it is very specialized. In this case, we're looking at the launching nose, which is basically two beams that are connected to the front part of the deck and they're braced together. You can see how there is no work in water, so it is environmentally friendly, and also how the construction area is relatively tidy for being a construction area. So it does have a minimal impact on the environment. And this technique has been used all over the world several times, so it has been time tested. So we're looking before at a launching nose. Here you can have a better idea of how it's made. It's, as we said, basically two beams attach the front part of our bridge that are braced together. So we saw before the bridge is built in a fixed facility, so it is sheltered from the element, but at the same time, also the area around the construction area is sheltered, so it is environmentally friendlier than other construction techniques. It's for this construction technique is usually easy to use local labor and material in support of local economy. And this because even if the local crew may not have a long experience with this construction technique, it is very repetitive, so the learning curve is fairly quick. Now you're looking at a beautiful bridge that was built in Scotland in 2008. For this bridge, the environmental impact, it was built in an estuary, and the environmental impact was a major concern during construction. And that is one of the reasons why incremental launching was chosen as a construction method. You can see there's no impact in the estuary. For this bridge, there was another big concern that was this area is in the migration path of some bird species. And there was the environmental concern in not disrupting this process. And that's why they wrapped in this green fabric all the areas where the workers were passing by. So incremental launching does have a minimal impact on active infrastructure. You can see down here, this bridge was launched over 11 railway lines that were active, and it was constructed in this area in 3 sections. It was then pushed in 3 pushes. So there is no active work over traffic. There were no speed restriction or traffic, and the railroads underneath, they remained electrified. So this construction method does have a minimal impact on maintenance of traffic compared to other construction techniques. So we said we were going to focus on cast-in-place concrete bridges. Let's see how we actually build a cast-in-place concrete bridge that will be incrementally launched. So first, we build our foundations and piers and place the launching bearings. While we do that, we start setting up our casting yard. Our casting yard will have a launch abutment, the curing supports, and a formwork that will be made by a soffit form, the outer forms, and the extraction rails, one per side. Then we place the launching nose on the curing area, and we make sure the back part of the launching nose is in contact with the front part of the first segment. It will not just be in contact, it will be securely tied to it. Then we set the rebar cage, we cast a segment. Once the segment is ready to be taken out of the formwork, we open the outer forms, as you can see here. We lower the soffit form, so now the deck is bearing on the extraction rails. And there are several ways to push ahead these bridges. Today, we will focus on one of the simpler applications, which is what you see in this rendering. So there are draw cables, which is these yellow lines that are anchored to the launch abutment and attached to these jacks. And then we have the back thrust beams. So these jacks go ahead and push ahead the first segment, freeing the formwork for the second segment. The second segment will be cast against the first segment, and the construction joint will have through reinforcement. So it is a fairly solid construction joint. This is how the first segment is pushed ahead, the second segment too. In the previous slide, you saw how the launching nose first was overhanging outside of the abutment. A few segments after is bearing on the second pier, and this is done to reduce the weight of the cantilever of the deck. A few segments after, it will reach, the launching nose will reach the last pier, and then we will have bridge completion. So now we just saw a simplified rendering of how a cast-in-place bridge is built with incremental launching. Let's see a real-life application. This bridge was built in Milan, in Italy. As probably most of you know, it is a very dense populated area where disruption of traffic is a serious issue. So you can see here the traffic going on while they were setting up the casting yard. And this is a real life application of what we just saw in the rendering. So we have the launch abutment, the curing support, and then our formwork. We want to have, in terms of room behind the abutment, it is ideal to have at least one span length. And this is to avoid problems with overturning. It has also been done with shorter room, smaller room behind the abutment, but there are some challenges that need to overcome. So if we want to talk about ideal situations, we want to have at least one span length behind the abutment. So in the second picture here, you can see how they placed the launching nose. It was bearing on the curing support, as we saw in the rendering. And at the same time, the crews were working on the formwork. You can see how the tracks that were used for launching this bridge, for putting together the segments, are fairly average tracks. There is no special heavy equipment that is involved with this construction technique. And this also has an impact on the traffic surrounding. We don't have heavy equipment that is moving on the roads that are surrounding the construction area. In this last picture, you can see how the launching nose now is here. So you cannot see it from the picture, but it's bearing on the first pier. And the first segment is part on the curing area and part is overhanging. The formwork is ready for the second segment with through reinforcement. You can barely see through the barricade. Workers are getting the cage, are getting everything ready for the second segment, and they're also working on the deck. You can see how the barriers are already in place. So at launch completion, the work that needs to be done on the deck is minimal. The bridge is pretty much ready to go. That also part of the reason why this is an ABC application. When we are done launching, the bridge is good to go. So the example that we just saw was a fairly simple application. For this construction method, the length of the bridge governs the industrialization. So we need to find the balance between the equipment that we want to use and labor investment that we want to have. This bridge was built in France, and it was a much longer bridge than what we saw before. So they invested in more equipment. You can see how here in the back, we have the first segment curing, and in the same time, they had more room behind the abutment. So they were also able of having workers setting up the rebar cage while the first segment was curing. So that once the first segment was pushed outside of the formwork, the rebar cage was ready to be moved into the formwork. So as you can see, there is no aerial construction, which is it's safer for the workers. Typically people are more comfortable when they work on ground. And when we are more comfortable, we are more accurate, and we're also faster. We said we were going to look at some limitations of application. For applying incremental launching to bridges, we need to have some geometry requirements. First of all, we need to have constant depth bridges, and this is just because of the nature of this construction method. We cannot go up and down following a variable depth bridge during launch. And the span length, the length of the bridges can vary from 350 to 5,000 feet. When we work with longer bridges, we can launch from both abutments. This has several advantages. It is faster, and also it's because we are working from both sides, and also it reduces the weight of the structure that is pushed forward. So all the maneuvers are much simpler. In this picture, you can see that it's two twin bridges. The first was completely launched. You can see how this used to be the casting area. So the disruption of the area itself was not tremendous. And also under the bridge, there is a fairly small impact on the surrounding area. Concrete girders and optimal span range from 65 to 230 feet. For steel girders, we can achieve longer spans, and we're talking about 160 to 550 feet. We can achieve longer spans with steel girders because they're lighter structures, so it's launching is easier for some aspects. When we have longer spans, we can use temporary piers. You can see here a temporary pier. We already saw launching nose, so when they were launching this bridge, the launching nose was first bearing on a temporary pier. Then as the bridge was pushed forward, it was bearing on the final pier, and so on. And you can see how here they're building the foundations and the temporary piers and the final piers. The geometry of the bridge has to be simple. So in this case, we're seeing two linear bridges. Incremental launching works very well with rectilinear bridges or with arches of circles. It has been used for different geometries too. Just when we look at ideal applications, rectilinear and arc circles are really what we are looking for. There are some design challenges, mostly because of the variation of the static system during launch. So during incremental launching, every cross-section is a support section and then a midspan section. So if we look at the section that is now here, before it passed through the pier, so it was a support section, so it saw some tension in the top and some compression in the bottom. Before that, it was a midspan section, so it saw a compression in the top and tension in the bottom. These translate into more material. So we are talking about 5 to 10% more post-tensioning and reinforcing than bridges cast on false work for concrete bridges. And for steel bridges, we are talking about a 7% increase in steel weight for the additional bracing and also the thicker plates that are needed. So where is the cost saving? The cost saving is on labor and equipment. And we all know the cost of labor is increasing higher and higher. Launch stresses, they need to be corrected in most cases. And we can use temporary piers. We can use a front cable stay system, or we can use a launch nose, or sometimes a combination of the three. You can see a unique launch nose is a little bit different than what we saw before. First is a truss before we just saw two beams just braced in between. But the main thing that I wanted to point out is these two jacks. These jacks at the tip of the launching nose are here because during design, they accounted for the elastic deflection that this bridge will see during launch. So by the time the launching nose reaches the pier, the top of the pier is at this elevation and not at this elevation. So being the top of the pier at this elevation, the jacks bears on the pier and they push up the launching nose so that now the bottom of the launching nose is on top of the pier and we can proceed sliding the launching nose and the jack on top. This picture shows you a very tall bridge with a temporary pier that was securely braced to the Jason pier and the launching nose. Now, it is very important to brace very well temporary piers, because for as much as we try to reduce the effect of friction of the passing bridge on top of the pier, the piers will still see some horizontal forces. So especially when we work with very tall structure, we need to avoid as much as possible concerns on stability. And you can see how the launching nose now is bearing on the final pier and is reaching the temporary pier. In the meantime, they were building the final piers for the twin bridge right next to it. So let's compare this construction technique with other construction techniques that can be used for similar span length. So for steel bridges, ground crane erection is a simple and inexpensive technology, and it has been it's used very regularly. So this makes incremental launching really limited to sites where we have very tall piers or steep abutment slopes, like you can see in this picture. So the advantages of incremental launching is that we don't have construction operation under the bridge, and we minimize all the aerial construction. For steel girders, based on the weight of the structure and the span length, we may or may not use a launching nose. In this case, they did it. You can see it here. Also, we talked about the geometry. We already saw an incrementally launched bridge that was completely rectilinear. This bridge is on an arc of a curve, of a circle. And you can see how also the launching area behind the abutment is set on the same curve. For steel bridges, at bridge completion, we can just launch precast panels on top of it, and that makes it an easy application. So let's compare incremental launching with the precast segmental construction. Well, precast segment, and you see an example of precast segmental construction. Precast segmental construction is faster. So if we take, for example, a span that is, say, 160 feet long, that can be built in 2-3 days with precast segment. It will take about 2 weeks for incremental launching of casting place segment. And this is just because of the casting of the segment. The launch itself doesn't take a long time. On the other hand, incremental launching is a much lower investment. You can see the equipment that is needed to work with the precast segmental construction. Also, for precast segmental construction, we know that the weak parts of the bridges are joints. With incremental launching, we typically have only 2 joints, and they are expand quarters. So they are close to points of contact fractures. So they have less demand. For going back to our example of a span that is 160 feet long, for precast segments, we'll probably have about 16 joints, 16 segments. So we don't have epoxy in the joints. We have through reinforcement, and this is in favor of uniform flexural capacity. There is also no impact on the ground. So here you can see how when we work with precast segments, we need room to start the segments. And we also need room to maneuver the segments, and we need heavy equipment to move the segments from the precasting yard to the area of construction. Let's compare this construction method with movable scaffolding system. Movable scaffolding system is adaptable to irregular bridge geometry. Incremental launching can handle some variations in the geometry, but it really works better with simple geometries. On the other hand, incremental launching is less expensive, especially when we consider mobilization or demobilization. In this picture, you can see an example of MSS. It is a less labor-intensive production, and with incremental launching, we have stationary logistics. There is no aerial work, and also there is no need for extra clearance under the bridge. So if you look at this picture, you can see here is the bottom of the superstructure, And then all this extra clearance is needed just for the MSS itself. And sometimes in urban areas, we don't have the luxury of having such a large clearance. We are pretty tight. So in that case, incremental launching presents some good benefits. So how do we push ahead these bridges? There are several technologies. As we said before, today we will focus on one of the simpler applications, which is the use of pre-sourcing jacks. So in this picture, you can see basically what you saw in the initial rendering. So we have the thrust beams, we have the pre-sourcing jacks, and we have the draw cables that are anchored to the launch abutment that is back here. This means that we have a short stroke. So typically we use two jacks. So one is pushing and the other is recovering. So then once the first one is done pushing, the second one is ready to push, and so on until completion. You also see two very important elements here, which are the guide beams. We do need guide beams to make sure that during launch there is no lateral drifting and we keep the bridge in alignment. Other ways of incremental launching bridges is rear thrust hydraulic cylinders and reaction beams, which will be a long stroke, or friction launchers. They're both very interesting technologies, although we will have to brush through them today for sake of time. So when we launch simple span or over a highway crossing, we could use an SPMT, and this is what they did in Belgium in this picture. SPMTs are great machines, although they do disrupt with the local traffic, and also they need a fairly flat surface or a regular surface to run. In this case, we were over a railroad, so the surface was definitely not regular, and the catenary was still electrified, so SPMT would have not been a good option. The bridge, so it is an application of ABC. The bridge was fully built behind the abutment and then launched in only one night. This was done in Italy, in Reggiolo, very close to where I used to live, and I was present during the launch. So this bridge presents a few unique elements. So let's look at them. It's a 4-cell box girder with a variable width. So the beams that are typically used for preventing lateral drift, the side beams that we saw before, they were not applicable for this bridge. Instead, they embedded a rail, and you can see it here in the middle of the bridge into the deck. During launch, the deck was supported under the interior webs of the box girder, not the exterior. You can see how before, until now, we only saw steel launching noses, and those are a more common application. In this case, they adopted a short concrete launching nose, which is basically just an extension of the interior webs that was post-tensioned. This was a very economical solution, and they had room to place a temporary pier in the middle of the railroad. You can also see how the temporary pier was braced to the abutment to avoid problems with instability, even if it's not a very tall pier and is fairly large. There is no interference with the railroad, and as we said, this catenary was energized throughout the process. So we said that incremental launching works great with simple geometry, which is true. It's not what they did for this bridge that was built in Spain for the 2008 Expo. First of all, I would like to point out how you can see how this whole bridge was built in this area. And the disruption of the area itself is fairly minimal compared to other construction techniques. And they're working right next to some tennis courts. So first, this bridge was incrementally launched more the traditional way. So it was just pushed. And then they used these 131 feet tall abutment mast So putting a temporary pier in the Ebro River was not an option. That's why they adopted this solution. So how does this work? The mast was supporting, is a triangle of forces. So the vertical force was supporting the front part of the bridge during launch, and the horizontal force was pulling the bridge during launch. And now we need to think that this bridge is bearing on a sliding surface. So they needed to control the slide, and that's why you see these cables at the back. So they had rear retaining cables that were anchored to concrete blocks, and this was just to control the launch. So incremental launching is ideal for rectilinear bridges and curved bridges. In this case, this bridge was built in Austria, and it was a widening of an existing highway, which you can see here. It is an S shape, so it was launched from both abutments. You can see the first launch here and the rest of the launch from here. So steel bridges are launched as continuous girders, but typically in our final condition, we don't want to have a steel girder that is this long. So we need to count during the design phase. We need to make sure that we have a splice over the piers where we want to have expansion joints. This way, the bridge will be launched as a continuous beam, but then at launch completion, we can go back and unbolt those splices over the piers where we want to have expansion joints. As you can see, this bridge was very tall over the ground, and you can see how minimal was this disruption during construction of the area surrounding the bridge. There is fresh snow right under the construction area. So low-level cable stay bridges can be also incrementally launched. Compared to balanced cantilever erection, it is a faster technology, it is less invasive, and it is a little bit faster. We work behind the abutment, we set up our structure, and then we started pushing. In this case, the leading pylon was supporting the front cantilever during launch, and it was also helped by these two launching nodes. This bridge was built in Canada, and it was opened in 2010. And the other pylons were laying on the bridge during launch, and then they were consecutively erected before opening of the bridge. Incremental launching has been applied to high-level cable stay bridges. This is a spectacular bridge that was built in France. It is the tallest bridge in the world, and it was incrementally launched. You can see how two leading pylons were supporting the launch, and they also used the temporary piers. So the advantages for high-level cable stay bridges is that the deck that is launched establishes a working platform for cable fabrication. It also makes it easy to access and deliver material through the deck. There is also, it's also easier to control the deck geometry, and there are less cable tension operation. So this bridge was launched with these two leading pylons, and then launch completion, the other pylons were erected, and then the temporary piers were removed. In this way, just having two open sections at the end at the two ends, we have less aeroelastic disturbance during construction, especially for such a high bridge. So the final spans were 1,122 feet, but the launching span, because of this temporary pier, were 561 feet. Incremental launching has been applied for construction of arch bridges. So the lower part of the arch is typically constructed in a more traditional way, and then the deck is launched into position. This is an older bridge. It was built in 1978 in Germany. There are several applications around the world of this same technique. So what are the advantages? We have longer approach spans compared to other construction techniques, so less piers, less foundations, less cost. We have a lower load imbalance on the arch, and we also only have one learning curve for both the main span and the approaches, because as we said, these sections are always the same. And you can also see here how they use a launching nose that was varying on two of the verticals of the arch, and the crane that was used for operation on the deck during launch. Incremental launching has been used for long span bowstring arches. This bridge is a Calatrava bridge that was built in Reggio Emilia in 2007. It's a 30-minute drive from the town where I grew up. And it's a beautiful bridge. And the way that it was incrementally launched is they incrementally launched the continuous span over temporary piers. You can see them here. And during incremental launching, the arch was lying on top of the bridge. At launch completion, they assembled and erected the arch. When the arch was ready, they removed the temporary piers, and that was it. This bridge is also built on one of the oldest highways in Europe. Incremental launching has been used in conjunction with bridge skidding for replacement of bridges. You can see in this picture, on the left-hand side, the bridge that needs to be replaced, and on the right-hand side, the new bridge. So these new decks were built behind the abutment and then launched and skid on the side, launched and skid on the side, launched and skid on the side. So you can see how after the segments are complete during the abutment, the launch itself is a fairly simple and quick operation. That's why we're talking about ABC. If you look at these decks, they're completed. You can see rails, they're already in place. You can see railing. So at launch completion of the new deck, the old deck was skid off of alignment, and the new deck was skid into position. Incremental launching has been used also for bridge demolition. This is a picture that was taken in France, and it shows you how the old bridge that you can see here that needs to be demolished was jacked up to make room for incremental launching an underbridge. So you can see the underbridge is this blue beam that it's now is in launching phase, but the end of the launching phase will be up to the end of the bridge. The bridge was then released onto the underbridge, and then it was keyed along the underbridge for incremental demolition behind the abutment, which is here. I don't have a full picture that shows the whole process. In this way, the area of the demolition was contained, and as a consequence, was also contained the impact on the surrounding environment. It does have this type of demolition does have a minimum impact on the surrounding infrastructures and also on traffic. You can see here a car that is driving under the bridge during these operations. So what are the optimum conditions for bridge launching? Bridge launching is great when we need to have minimal impact crossing, but there is overactive infrastructure or sensitive areas or areas where the impact on the environment is a real concern. Urban bridges where we need to, clearance under the bridge is tight. Works very well with minimum length bridges with a simple geometry. It can be adapted with more complicated geometry, but if we look at this application and it's at its best, when we work with a simple geometry, it's better. Construction technique has also been applied to cable stay and arch bridges where the area can be partially disrupted or when we work aerially on very, very tall elevation. In this picture, you can see the launching nose. You can see the deck, how it was completed. There were railings. There were also sound barriers during the launch. You can also see the temporary piers. Temporary piers was anchored to both abutments with stake cables that were encased in steel tubes. And this because they were trying to avoid the risk of a broken strand falling on the catenary, because these catenaries that you see here were still fully energized. And at last, I wanted to show you the steel box girder, because well, we haven't seen other steel box girders in this presentation. When we launch bridges, we want to have sections that have a good torsional behavior. So if the section itself does not have it, we need to bump up the bracing. You can see a little bit of a different launching nose that you saw in other pictures. For steel bridges, we said that we can, at launch completion, we can incrementally launch precast panels on top girders, again, to minimize aerial construction and also to make the construction faster. You can also see, again, how minimal is the disruption of the local environment around the bridge. You can see daisies right under the bridge that is built. And this is it for today. Thank you for your attention. I think that now we have time for questions, but if you can think of something later, just you have my emails there, so feel free to reach out.
Right. Thank you, Chiara. Very interesting. It's almost having a 10 webinar jammed into one. Many interesting concepts. So at this point, we are going to turn it to Paul Lyles, Jugesh Kapoor to moderate the question and answer period. To our audience, because of the number of the questions that have come in and the question that were asked, we are going to go up to 20 minutes after the hour.
All right, thank you, Torrid and Chiara. Really, really an interesting presentation, and we've got a lot of questions so far, and we'll probably get some more. Let's start off with some that came in pre-webinar questions. And
okay.
The first one here is came in, and it was like, what are the key aspects that make the bridge launching construction technique an accelerated bridge construction method?
So incremental launching is an ABC technology, especially when we talk about simple spans, because whether we have a steel section or a concrete section, once the section is ready to be launched, the construction itself just happens in a few hours. It has also been used in conjunction with other ABC technologies, as you saw in this presentation, like skidding.
Okay. And some of them, it almost looked like you couldn't do anything else. The restrictions were so so tight.
That is true. So sometimes it takes, it's probably accelerated just because figuring out a different technology that could work in the same situation will take more energy and effort and time to adapt rather than just using incremental launching.
Okay. Another question that came in beforehand were do you have any thoughts on why this method has not been or hasn't been used more in the United States?
Well, there are no scientific studies or about this. So this is just my personal speculation on why. So take it for what it is. I think that in other parts of the world, this technique has been seen very often. In the US, it's not seen as often. So sometimes it doesn't even cross our mind. But that also happened with other ABC technologies that now are way more popular. So will this technology become more popular in time? Probably, I hope so. It's hard to tell from now, but I don't see why not.
Okay.
We do have the materials, we do have the technology and the knowledge to make this work in the country. That's why I don't see any limitation on why it shouldn't become more popular.
Okay. Another question from beforehand. It says, for roadway infrastructure, what are the approximate boundaries to assume for roadway and construction easements?
So I tried to address this a little bit in the presentation. We typically want to have at least one span length behind the abutment to avoid possible problems with overturning. Now, if that's not a possibility, we can investigate other solutions. They will not be optimal, but they will still work. Ideally, we want to have at least one span length. Although, if it's a long bridge and we want to increase productivity and make this technique faster, if we have more room, better, because especially for cast in place concrete, while one segment is curing, another crew can prepare the rebar cage right next to it, and then everything gets faster. But do we need to have it? No. And sometimes if the bridge is short, it's not even worth the investment.
Okay. And you kind of answered this a minute ago. It came in beforehand. Can this technology be used for simple span bridges? I think you said it could.
It is, yes, it is. It's a great application of ABC construction. The whole span is built behind the abutment. When we're working with simple spans, typically we have either a long launching nose or a temporary pier, but it all depends. For this construction method, everything needs to be calibrated based on the equipment that you have, the construction restrictions, and the section that we decide to use. So it is very adaptable. There are different solutions that can be implemented.
Okay. Another one came in beforehand was, can you clarify the significant difference in stresses in each section during the launching and final design and achieving economical design?
So as we launch bridges, if we look at the sections that are here now cantilevering, they were over the pier before and they were in mid-span. So there is a variation of stresses that is due to the variation of the static support. So when we are over the pier, if you're looking at this section, it will see some tension in the top and some compression in the bottom. When we are in the middle of the span, the section will see compression at the top and tension in the bottom. Now, in terms of materials, these translate into more rebar and post-tensioning. For concrete bridges, we are talking about 5 to 10%. For steel bridges, we're talking about a 10% increase for bracing and also thicker plates. Now, the economical part is what we save on labor, that we know is a very expensive part of our construction, and also the equipment, because it's fairly inexpensive compared to other construction techniques.
Okay. Question from beforehand, using this technology, what are some of the span weight balancing limits?
This is a tricky question. It really depends. It really depends on the span length. It really depends on the launching equipment that we use, the type of launching nose that we want to operate, or whether we want to use a front cable stay system. The tricky part is that when we go to longer spans, we end up with the taller sections, and that sometimes is not aesthetically pleasing. So it is a balance that needs to be considered beforehand. There are no written limitations. You sign these presentations, a good variety of different types of bridges with different span length that were incrementally launched. All of those had a different balance that was considered during incremental launching.
Okay, and I guess along the same lines is the question about what's the overall maximum weight of a typical incremental launch? I think that could be varying too.
There is, yes, that is varying. Although if the bridge is long and we have room behind both abutments, when the bridge gets very long, it gets heavy. So we can launch from both abutments. That reduces the weight of the bridge that is moved. But again, it's a balance between our span length, the equipment that we have, and the section that we also need for final design. There are not just the launching stresses.
Okay. A question came in beforehand, and for this technology, what is the effectiveness of using fiber reinforced concrete for bridge deck slabs?
So going back to the precast panels, It's pretty much the same advantages that we have for regular steel bridges because we put the precast panels at launch completion. So during launch, we only launch the girders. We don't have any deck on top of it. After that, it's the advantages of fiber reinforced or the disadvantages of fiber reinforced are the same exact that we see for more traditional construction types.
Okay. A question came in beforehand, and I'll add to that a couple other questions, but that are involved the bearings. What type of bearing pads or sliding elements are typically used during bridge launching activities?
So launching bearings are very interesting. I think that we should probably have a presentation just on launching bearings and also the thrust system. Very interesting technology. So I'll try to keep it as short as possible. We need different launching bearing whether we're working with a concrete section or steel girders or steel U-girders. And this is because of the different weight of the structure that we're moving, and also because of the flexibility of the section. So for concrete, we have the simplest application. So typically, a launching bearing for a concrete bridge kind of look like a sandwich, where we have a concrete block and then an elastomer, and then we have a plate that is either steel or concrete, and then a layer of polished stainless steel and the neoprene pads, and then the deck on top of it. So the weight of the deck move the neoprene pads on top of the layer of polished steel through friction, and that's how we incremental launch concrete decks. For steel girders are lighter and they're more flexible, so they require a little bit fancier type of bearings. So typically we want to avoid concentration of stresses, so we end up with long support surfaces to distribute stresses, and also the bearings need to rock because of the flexural rotations of the girders during the launch. So at launch completion, the deck is jacked and then is lowered into the final bearings. And I could go on much longer, but maybe if whoever asked the question wants to reach out, and we can talk further later on.
Okay. Now, and then there were two other questions associated with that came in during the presentation. One of them was what bearings are typically used. You kind of described those. They were pretty complicated. They're not manufactured proprietary, like a bearing company. They're specially made for the individual situation.
It depends. So for concrete bridges, it is simple enough that it's adjustable to several situations. For steel bridges, they tend to be a little bit more customized. For steel bridges, we also need to consider that when we launch steel bridges, we need to customize the splices of the girder, because we cannot have bolts and nuts in the area where the launching bearing is. So our splices need to have an area in the middle where there are no bolts and nuts, because we can slide.
And then the other question on this was, and you did mention that it was lower down to a bearing that was the final bearing. It was not the same as the jacking bearing.
Correct.
Yeah. Okay. And then we had another question that came up on this. It was kind of interesting. It sort of involves this, but for the checking of the stability of the piers during the launching, what longitudinal force do you consider at the top of the pier? Do you consider the weight of the segment multiplied by a friction factor?
Yes, but also we need to think that we are trying to reduce as much as possible friction. That's why we use all those neoprene pads that slide on those polished surfaces. So we're really trying to minimize this longitudinal force as much as possible, for both the sake of the pier, but also to facilitate launch. Friction is a major retainer, especially when we work with these heavy weights.
And the question asked was the coefficient like 20%? He was asking what's the magnitude for the friction coefficient.
Oh, I will have to look up the
Okay,
the
that's
exact
fine.
number.
Okay. All right. We've answered all the questions that came in beforehand, and I'm just going to go down some of the ones that have come in during the presentation. These are pretty good. For slide 5, and this question happened several times, was launching permitted with any live load traffic down below? And you did mention one where that was going on. So is that common, or is that just during the actual launching operation? Do they?
So it really depends. It has been done. You have seen some applications where launching was done on active traffic, and there were no concerns from the local jurisdiction for those type of bridges. In other cases, it was preferred to stop traffic during the launch operations and then restore traffic. Now, when we talk about launching operations, we're talking about hours. So even if they decide of, sometimes they will stop traffic, say this bridge was built in 3 segments, so they will stop traffic after the launch. They will launch a segment. During the launch, they will stop traffic. While they're building the second segment, traffic will be ongoing. Then they will stop traffic for a few hours, launch the second part. So now we have the bridge up to here, and traffic will be going while they're building behind the abutment. And then they will go to completion without traffic underneath, and then reopen into traffic. Now, is this necessary? No, it has been done both ways. It really depends on the level of comfort that we have.
Okay. A couple questions here. Let's see. Performing segments, is it required to cast the soffit forms with some sort of grease or other bond for the rails?
Okay, so when we extract the segment, we are just bearing on the extraction rails. The extraction rails are treated to make slide easier.
Okay.
And the lower part of the form is lowered, so the deck is just bearing on the extraction rails.
Okay. And the question on the extraction rails, after casting a segment and lowering the bottom soffit forms, is the just cast segment supported continuously on the rails or at discrete points?
It depends. It can be done both ways. It can be, in this picture, you can see it is continuously supported. Sometimes we use launch bearings. There are several, again, this construction technique has been used all over, and it is very flexible. So for some of the launching equipment is dictated by preferences, other times is dictated by what is available. So incremental launching has been applied with a good variety of different technologies.
Okay. Does the length of the move set or the launching nose, excuse me, is the length of the nose set based on span length, or is there a specific length and the specific length of the nose, and then the span length is adjusted accordingly to match?
Well, we need to balance the site restrictions for where we can put the piers, the weight of the structure that we're moving, and also the weight of the launching nose. That dictates the length of the launching nose, and also the stiffness of the launching nose. So that dictates the length of the launching nose. So based on the span length and the weight of the structure and the weight of the launching nose itself.
I think they were trying to see if maybe they could use the launching nose over and over again for different jobs.
They can. Actually, it has been used over and over for different jobs. Okay. Just before doing it, we need to do our math and make sure that numbers turn out well.
Okay.
Also, because during launching, there is no, the launching nose is not ruined. So at the end of launch, all this is easily reused for a different project. We just need to make sure that we have a length that is appropriate. But in this case, we have 2 beams. We saw for other bridges, we were just having a truss, so that we can just shorten or lengthen the truss.
Okay. how is the launching nose attached to the segment, since it appears to require a strong moment resisting capability?
It is bolted PT to the segment. So there are several ways to attach it. It is definitely very securely attached to the segment, depending on whether we are using steel bridges or we are using concrete bridges.
Okay. Another bearing question is, what is the footprint size of the temporary bearing on the piers during launching? And in other words, do you have to make the pier bigger or anything to accommodate the temporary bearings?
No, typically you don't need to make the pier cup larger to accommodate temporary bearings. As I said, we could spend like a full other presentation just on temporary bearings and the thrust system. But to shortly answer this question, no, we don't need to make the pier cup larger to accommodate them.
Okay. Now, we had a couple questions that came in about, can you use it on curved bridges? And you showed some slides where you were doing that. And it
Yes.
says, does the incremental launching construction method adopted when there is a horizontal radius? And the real question here is, if yes, when you just said yes, what is the threshold for a horizontal radius below which the method could maybe not be used?
I don't think there is a threshold. I think that the bigger concern is to have the radius constant. This construction technique doesn't adapt well to varying geometries. So as long as the radius is constant, I can think right now of a limitation on the radius itself. We need to be careful with vertical slope. If we have, and that also ties back to the previous question on the weight that can be moved. It's not just a matter of weight, it's also a matter of longitudinal slope that needs to be overcome, because that increases the weight that needs to be moved. There are some limitations, not limitation, but we need to be very careful when we do incremental launching downhill, because all these bridges are on sliding surfaces, so we need to be careful to be able of restraining the bridge during launch. So I don't see, like, once the curvature is continuous horizontally, I don't see right now I can think of a strict limitation on the radius itself. But I think that more challenges in general come from either a various geometry or the vertical curvature that needs to be accommodated, which it doesn't mean that bridges cannot be launched on a steep vertical curvature, just it increases the weight that needs to be moved. It makes the construction a little bit more challenging.
Okay, a couple more, and then I'm going to turn it over to you guys, because we're continuing to get questions. We got a whole lot of them. Were most of these launches anticipated as the method of construction? Was that in the plans, or was it left up to the contractor to decide?
I'm not sure. I will say that most of the times it is anticipated, and it is also discussed with the contractor. In Europe, design build is very strong, so there is always a good collaboration between the designer and the contractor. I think a little bit of both. Now, bridge by bridge, it probably in the initial investigation of the project, they evaluated, as we do everywhere, the pros and cons of different construction technologies for the specific application.
Okay, well, it's real interesting. I'm going to turn it over to Jugash, and he's going to ask a few more questions. Jugash?
Thank you, Paul. Chiara, the first question I have is, what was the launching technique preferable over a launching gantry crane for the bridge in Scotland?
We're talking about this bridge, correct? So in this case, yes, incremental launching was preferred to other construction techniques because of the smaller environmental impact that it does have. It was, as I say, it was a very sensitive area for an environmental standpoint. There was a major concern in not disrupting the environment, both in water and outside of the water, and on top of it, also the migratory movement of the birds. So most other construction techniques would have had either more impact in the water, or the construction itself would have been of the deck would have been more invasive. So this was considered in the design and in design phase. Actually, this bridge is the winner of a Saltire Engineering Award.
Okay, thank you. Next question. For forming segments, is it required to coat the soffit forms with some kind of grease or other bond breaker?
I think we already addressed a similar question when we're talking about the extraction rails. But if whoever asked the question needs more information, feel free to reach out. We can talk about it.
Okay, next question. After casting a segment and lowering the bottom soffit forms, is the just cast segment supported continuously on the rails or at discrete points?
We already discussed this, but it depends. So it can be supported just on, okay. So in this case, once they lowered the soffit form, the deck was continuously supported on the extraction rails, although it can also be supported on launching bearings. It depends. There are several different technologies to push forward these bridges. This that we're showing here is one, but several other techniques has been used throughout the year in several different countries, and it depends on sometimes also the equipment that we have available on site, or the length of the bridge, also the amount of the industrialization that it's worth to spend in.
Okay, thank you. Next question, how is the launching nose attached to the segment, since it appears to require a strong moment resisting capability?
So the launching nose is attached through, depending on whether we are attaching to steel bridges or concrete bridges. It's either bolted or it's post tension into the bridge. And it's true, the connection between the launching nose and the front part of the segment needs to be very well secured.
Okay, thank you. Next question. In the case of pre-stressed superstructure, how can we use this construction method in the case of precast box girders with balanced cantilever construction method, or the concrete box girders need to be cast in place with this construction method?
So no, I mean, if we can use precast box girders, we do lose some advantages, which are the less joints, and also the movement of small tracks, and having to store segments. If we want to use this construction technique with precast segments, we need to be very careful in designing the launching post tensioning to make sure that we don't have joint opening during incremental launching.
Okay. Chiara, I'm out of time, but there are a number of questions that remain to be answered. I believe the answers to them will be posted on the website. So with that, I'll turn it back to Adarad. Thank you, Chiara.
All right. Thank you, Jugesh. All right. Thank you, Chiara. It was a very informative webinar. So on that note, we are going to conclude our webinar today, and hope to have many of you back with us again on our next monthly webinar, which will be on Thursday, April 20. So until then, so long.